So, it's already been said, like this talk is about sharding graphs and how to query them. And because this talk is only for 20 minutes, we can evaluate all the approaches, all the possible approaches. So we are going to focus on one that we sort of like found very interesting and yielded a very good results, and we implemented that. And that's basically splitting your graph database into disjoint subgraphs that basically have any physical connections between them, and then introducing basically query language extensions that will enable you to easily work with those graphs as if it was one graph. And to make it more interesting, basically we are going to show this concept on an example, and the example is going to be the LDBC social network benchmark. So basically, LDBC social network benchmark is a benchmark that emulates a social network, and it defines the data set, data model, and the query that is basically part of that benchmark. And what is interesting about it is that the data set the graph is very strongly connected. Basically, we have a colleague who is sort of an in-house expert on LDBC benchmark, and when we told him like we want to basically do a sharded version of LDBC benchmark, he was like, "You are crazy. That can't perform well," and we sort of proved him wrong. So first, like before we go into the sharding, let's short introduction to the LDBC model. So we are in picture. It's a little bit blurry. So basically, it's a social network. So you have people and they have some relationship. They basically have a relationship between them. That's basically the core of every social network. Then the main workload that the people do is basically post messages in forums. So so you have forums which have members and owner, and also basically the main workload is that people put posts in those forums, and also they can comment on the posts and comment on comments. And of course, each post and comment has an author, or they also can be liked by a person. And each forum post or comment have tag, basically representing its content. Tag have a class hierarchy, basically they are in a hierarchy, and people can express interest in some topics, basically saying I'm interested in topics marked by those tags. And also people live in cities are located in countries, and each message, meaning post and comment, have also basically country where they were created from linked to them. And because like sharding, as we learned, is not just like about the data, it's also like about the workload that you want to perform. So basically you have to, when you want to shard something efficiently, you should look both at your at the data and also basically what you want to do with the data. So just like example, how a typical LDBC query looks like. First, in this example, it's a query 9 from the interactive complex category. And given a start person, you are looking for messages created by friends of that person or friends of friends. And the messages have some filtering criteria. They have to be created before a given date. So basically, this query kind of traverses a quite big portion of that graph. So the interesting part, so how we, just for inspiration, how we decided to shard this model. What is interesting about the approach we took to sharding, we basically like evaluated many approaches, and this is sort of like the model we came up with. What is interesting about is that is asymmetric. Basically, that means that not all the shards basically have the same data set. We have always one person shard that basically contains all the information about the people and basically the relationship between them. And then we have something that the rest of the shards are what we called forum shards. Basically, we distribute all the forums on the remaining shards. This is a big advantage because the forums are sort of a forest, so from graph perspective, and they don't have any interesting relationships between them. So this can be done kind of easily. For instance, using some kind of easy sharding functions. For instance, modulo forum ID. What's also interesting about this model is that basically person also sort of is represented on those forum shards, but they are sort of like not full representation of the person. It's basically just a node with person ID. You can sort of like see it as a like a proxy node or a reference to that person shard that actually contains like the full information about the given person. And also like for efficiency, some of the data are replicated like across all shards, which presents the location structure and the tag structure, which isn't such a big problem because the data set, this is a very small part of the data set. Basically like from the data volume point of view, the biggest part are the messages and the forums and that structure. And now when we have the data model, the interesting part, like how we can easily query that and work with that.
Right, so assuming we have our data now split over some set of disjoint subgraphs, how could we use Cypher to query across those? So we introduced two new constructs to Cypher, which are use and call subquery. And use quite simply dictates what subgraph a certain query part should go to. So the match here will go to the graph A graph and match only from that graph. And the use is allowed for each sort of query part. So in a union, for instance, you can select two different graphs. And the other construct is the call subquery clause, which is very similar to calling a procedure in Cypher, except it's an inline Cypher query that is the body of the call. And like any Cypher clause, this call block, the subquery, gets executed once per incoming row. So in this case, it's going to get executed 3 times, once for each value of x, as we unwind this list of 3 values. And the return values, the return columns of the subquery, are then exposed and available as new variables in the outer scope. So here we return the number of movies, and then we have access to the number of movies variable outside of the subquery. And these can then be combined in interesting ways. So we can have the use clause, of course, to dictate on what subgraph the subquery should execute against. So in this case, we just go to some graph A for the duration of this subquery, and then we return to the outer context once it's finished executing. And we also have support for correlative subqueries, meaning that the subquery can access variables coming from the outer scope. And we have opted for an explicit approach here where you need to specify each parameter that you want to, each variable that you want to access inside. So that looks like this. With x imports the x from the outer scope. And the most powerful use of call and use together is the dynamic use lookup. So where you can go to a different subgraph depending on data that's coming in. So this is again sort of a correlated subquery because you sort of choose what graph to execute against based on the value of this graph ID variable. So each execution of the inner of the subquery goes to a different subgraph. Right, so let's look at this in the context of one of the LDBC queries. How would the Cypher actually look to implement one of these? So this is interactive complex number 6 from the LDBC queries. And it reads like this. I've expressed it in some sort of pseudocode here. So we're given a person and we're given a tag. We want to find friends and friends of this person. Then we want to find the posts made by these friends that have this tag. And then the final result is basically all other tags of this set of posts that we have found. Okay, so how would that look? So we would start with a subquery that goes to the person shard. Remember, we have the persons network in one shard, and then we have sort of different forum shards containing the posts and the bulk of the data. So we go here, we match persons and friends of friends, and then we return just a collection of the friend IDs. So now we've taken care of the friend of friends part of this query. And then we continue by going to each of the shards, each of the remaining shards, the forum shards. We import this friend IDs to each of them, and we basically reboot the query at this point by matching for friends where the ID is in this friend IDs collection. So it's sort of a manual passing of data through to the different parts of the query. This is all right. And at the end, we do a final global aggregation. So what we actually need to return is the tag name for each of these tags that we found, and then we aggregate on the post counts for all of those. So we did a local aggregation first on each of the shards, and now we do another global aggregation of those already sort of summed number of posts. And then finally we limit everything to 20 because that's what the query expresses. And using this sharding scheme, most of the queries in the LDBC interactive complex set of queries can be expressed in very similar ways. This is another example where the first part is quite similar. We again go to the person shard and find friends of friends. That's a common pattern in these queries. And we then go to the forum shards, but this time performing some other matching and some other kind of aggregation. All right. That's basically all that we have. For further reading, we have a blog post out about our implementation of this inside of Neo4j. The language constructs are released under the Open Cypher project, and those are open sourced. The implementation, the engine behind this sharding scheme is not yet open sourced. We're hoping that parts of it are going to get open sourced in the future. Right. And Michael has asked me to say that Neo4j is currently hiring engineers in all in all positions. Right. Thank you.
Time for questions.
Could all this declaration of how you want to use the shards not totally be hidden for the user? And you just fire your old query, and the query processor knows how the graph is sharded, and then compiles the simple user query in the extensive query like you show.
Right. So the question is, couldn't this directing what shard to go to in the queries be solved automatically by by the system. And yes, it could, and we're sort of exploring things like that. But Neo4j is currently schemaless, and we're looking at solutions of introducing schemas that would dictate where data lives in shards, and going that route to eliminate these sort of annotations of where to find your data.
More questions. What else can you do with the fabric approach?
I'm glad you asked. Right, so we saw what else can you do with the fabric with this sort of setup. So other use cases, of course, is like data federation, where you might have a bunch of already separate databases, and you want to run some sort of analytical queries across all of your data, across your, let's say you have a microservice architecture where you have a bunch of different Neo4j stores that are not connected. You might run queries like this to aggregate data across all of them. Yeah.
More questions? Cool. Thanks, Tobias, Patty, for the talk.